Welcome to the first technical video for Chernobog. This is a game, huge, ambitious game that is in development. You can follow the general development on the other channel, Intrinsic Games. Check it out in the description. But today I wanted to talk about character creators. We're making this game to be sort of like an RPG with a ton of simulated NPCs in the world, right? So we need to actually have a character creator that's really deep with a lot of customization, and it needs to be super efficient too, right? Because we want to be able to render potentially hundreds of characters on screen at one time. So we can't have like a whole bunch of draw calls or like too many polygons or anything that's going to bring down the frame rate. So what I wanted to do was just give you guys a little overview of kind of what I had to do to build this system from scratch in Chernobog. So first, be a really talented artist. Luckily, I have some artists on our team, Cindy and Talia, who are able to make crazy stuff like this. I obviously wouldn't be able to do this, but obviously you can make models like this in Blender or whatever tool you want to use. So here's the base model for our female character. Currently naked. Let's put some clothes on her. So I have this big editor that I've built with all these different, fields that I can edit so that we can actually test things. Because anytime, especially when you're making your own engine, anytime you make a feature, it's good to always build tools alongside it. Because if you don't, then you're going to find like debugging and just making changes to the actual data fields a huge pain. And mGUI, of course, is a really good way to do that. I'll have some other videos on mGUI on my channel as well. So first, right off the bat, what I want to explain is that a modular character system is all about swapping parts out and doing morph customization and then like doing things like color shifts and color changes. So as you'll see, I actually swap these body parts out. If I take these back off and I go to edit submesh here, you'll see this model is actually split up into many different submeshes. There's actually 8 submeshes that make up this whole thing. And the reason it's not one big submesh is because we want to actually make this a little bit more efficient. For example, if you have a leather torso on, we want to be able to swap out your entire torso model with the leather one and not actually display the vertices underneath. Additionally, if you wanted to like actually have armor on that was really skin tight and you didn't do this, you would get probably some Z-fighting or some clipping that would happen, especially when you turn morphs on. So by doing that, if I put this leather chest on here and some leather pants, some leather leggings, you'll see that it actually cuts away the body here. So this already is going to reduce our vertex count. And then these armor assets, the legs and the torso here, they can just specify which body parts they're going to be covering. That gets handled in a different editor, essentially. So our artists will kind of author all of these different pieces and we'll classify them into different categories. The actual asset data for these has some metadata attached saying like, hey, this is armor of this type. It goes in this equipment slot, stuff like that. We also have hair and other things. So let's put some hair on her so she's not bald. And let's give her some eyebrows so she doesn't look creepy. Just like with the armor, these are just modular pieces that the artists can make. We have actually a ton of eyebrows because they're super easy to author. And these, unlike the armor, these can actually just go on top without covering up any of the underlying body here. These are just attached to the head bone. You can see we actually have, of course, a rigged skeleton here that can play animations. Let's just play the idle animation. And it's just affixing to that bone. And then what you'll want to do as well, of course, is to do what's called weight painting, which is where the artist goes in and designs sort of how the hair or the armor and such is going to deform with the bones. That's something you do normally just when you're making any 3D model, but you have to do the same thing to the hair. You need to weight paint the hair to the body. For things like eyebrows, you don't really need to weight paint these, but you do need to attach morphs to them. So let's talk about what morphs are. So morphs, also known as blend shapes, also known as shape keys, I think in Blender, are how you actually get the sort of customization that you're used to in these character customizers where you can move things around. So if I go back to appearance and I'll go down and start messing with the body a little bit. So I can change a whole bunch of different sliders. Like I can make her fat, I can make her super muscular, and these can be combined. I can make fat and muscular if I want to. And then, all the things you would want, you can change in the body. Same thing with eyes, right? All these different things are completely tunable. And the way this is authored is the artist in Blender will create what are called like shape keys. And it's essentially just taking your model and squishing it around. You don't change the topology at all. Let me reset all this again. And I'll put on, let's do like wireframe view. So this topology here, the actual triangles, let's take these off so it's the base body. They will not change between morphs because you're just moving the vertices around. And what that means is you have a sort of a 1-to-1 mapping between the morph shape and the original body. And then you can just do linear interpolation, which linear interpolation, I'm sure you know, is just like you take one thing and you blend it to the other thing linearly. So if these are two vertices, like this is our fat vertex and this is our skinny vertex, or our standard vertex, a 1 value would be fully fat and a 0 value would be fully skinny. And because it's linear interpolation, you can actually go beyond if you want to. You can actually overdrive your morphs and go to like 1.5, or you can go to even negative numbers. Like I can show you that. It looks kind of silly, but let's put the wireframe back off. So like with body morphs, if I was to say, hey, this is maximum muscular, but say we want to make the Hulk, we make that a 2, it kind of overdrives. And it breaks because this isn't what the artist intended, or we can go -1 and make like super emaciated characters, right? You wouldn't do that, but because it's just blending between morphs, you can kind of tweak these. I actually have a little bit of a underdrive that lets you kind of take morphs in the opposite direction. And you can sort of decide with each morph how much leeway you want to give people on how far they can kind of change these things. But obviously, like there's lots of things you can change. We can do a randomization that gives you just random characters. And the random characters are often very ugly, right? Because you're just completely randomizing the morphs. But sometimes it actually works out pretty well. And if you're just trying to make like random peasant NPCs, this works really well. If you want to make more heroic NPCs that aren't typically ugly, you would probably make some pre-built morphs and then just randomize those a little bit so that it kind of stays true to like the heroic characteristics you would want for a hero character. We also can do sort of procedural texturing things, obviously. So with the skin, for example, you can't just like darken it. It just doesn't really work out. Like you lose the kind of color depth. I don't really know how to explain it because I'm not an artist. But what our artists did is, let me put the skin tone back, is gave us 4 different, if I go to, I believe, variants, I can switch between these. So 4 different skin color textures that are sort of the 4 base textures. And these are handmade so that they can control the values and the hues and things and make sure that you don't, like when you just darken it, you don't lose that detail. And then we can just procedurally blend between those 4 to give you that smooth kind of color tone. Same thing with the hair. With the hair, actually, we just decided it's okay to kind of lose some of that detail. It actually works out okay. What we do is when you drop the value here, it increases the saturation. So you can see that like it gets kind of deeper purple, starts at pink and gets deeper purple when you make it darker. And then of course you can change the hair hue, right? You can make some really crazy weird colors that we may not want people to be able to do, so we might kind of make a palette system instead of that. And then you can of course change eye colors too. So here is the color mask for the eye. So this goes on top of the eye material essentially. And each of these colors will represent a different, basically, color channel. So we can decide what we want to color change just based on what color it is. And that's how we get these 3 sliders here for iris, pupil, and sclera. So if I just change like sclera value, I can give like black outlines to the eyes. I can change the hue of that, give you like red bloodshot eyes. You can change the hue of the actual pupil itself, make it maybe super dark. And you can, of course, change the value and hue of the iris as well. It's really cool. Those color channels you could use for armor as well. You could put it on hair if you wanted to have certain parts of the hair that have highlights or things like that. And then in the shader, you just select which thing you're coloring based on that. It's very, very simple. And of course, because the eyes are 2 separate models, you can do heterochromia if you want. You just store those different values for the different sliders for each eye, and you just pass those in separately. So that's sort of the feature set of what we have with all this customization. But there's more than just what it looks like. We also have to make sure it runs really efficiently. Like obviously what you wouldn't want to do is take all like 40 of these sliders or whatever, and in your shader, have all those different meshes passed into vertex buffers and then, blend between those on the fly in the shader. That would be just way too expensive. That's too much bandwidth. That's too many operations. It's terrible, right? What you actually would want to do is bake this down. So what happens is every time I randomize, this is going to bake down a new mesh. And it's not rebuilding the entire mesh. We're keeping the same vertex normals, even though we probably should change the vertex normals. We'll just see how it goes. Keeping the same UVs, right? Same metallic roughness, PBR kind of values. The only thing that we're storing is the actual position. And we're not just storing the position like as XYZ 32-bit, right? We actually can compress that down because these characters are pretty small. You don't need the full 32 bits of precision to represent the position. So you can actually compress these morphed characters, the actual positions, to be pretty small. I'll show you what that looks like. So I'll give you a little look into the code. It'll be the first kind of engine code I've showed. Here's just a little block of code here. This is in the sort of like morph updating function that is going to actually update the morphs for a particular mesh. So this may happen if you're building it for the first time or you're moving a slider or something like that. So like we have this bake function that takes our model. It's going to give us out just a bunch of float vertices, right? These are vec3s. These are not compressed yet, of course. And then the input is just a morph weight map, which is just a flat map. with a string to a float. Excuse my custom types here. And what we do is essentially just loop through the morphs, right? Check if it's a morph that exists in the map, because this map is specific to our current model that we want to render. So not all morphs are actually going to be there. Not all morphs are going to have non-zero weight, right? If the morph has 0 weight, you don't want to do anything with it. And then we just kind of loop through all of it and accumulate these morph values in our vertex data, which is, it starts out with just a copy of the base vertex data, right? And then we're just adding on additional vertex offsets with a certain weight. So we're basically linear interpolating each one away from the base and adding it additively onto the original base vertex data. A lot of to-dos here, of course. And then once that's baked down and we have the sort of uncompressed representation, then we can compress it down directly into our sort of GPU data buffer, which this is, I believe, a mapped buffer. Yeah, so this is going to be a mapped OpenGL buffer to some GPU data. And as you can see, it's a buffer of 64-bit uints. So we're compressing down 3 floats into essentially 2 floats, right? So we're getting a sort of 66% compression ratio. And all the compression does is we're taking 21 bits for the X and the Y, and then 22 bits for the Z channel. So, you're just kind of turning this into an integer and then packing it all together, sending it to the GPU and your shader, and then your shader is going to decompress on the other side, and then you'll have your positions. And because these are such small models, you get plenty of precision range for this. We have this like precision range here, like, hey, the character can be up to 5 meters, I guess, right? This could be even smaller. You can just kind of tweak this value to get to change your compression ratio based on how big your model was going to be. Like, you can use this to compress other things. It doesn't just have to be like a skeletal model that you're compressing with this. So additionally, we need to be able to, of course, render these without having a draw call or multiple draw calls per model. It's obviously a big problem. Now, there will be not a single draw call for everything all combined, but what we can do is batch everything together using what's called indirect rendering. I'll touch on that a little bit more. Probably can do a whole video about indirect rendering. It's an amazing thing that really boosts your performance to the next level. It's like instancing plus, essentially. But first, there is an additional feature that I didn't cover, which is changing the actual like shader that we use for each of the objects. So when I go to like edit submesh here, there's a shader here that is selected. So if I go to like the eyes here, or maybe the hair, the hair's not here because hair is an additional thing. Well, if I go to the eyes, I can change what shader is used, and it'll allow me to pick any shader that is configured to be a skeletal model shader. It's another just kind of metadata thing that is added. So I can do like wireframe. Actually, I guess that doesn't work in this view. But you can change the shader, and then what'll happen is it's 1 shader per draw call. So depending on how many different shaders you use in your model, that's how many draw calls you're going to end up with your scene. So in this case, we have hair, we have stencil hair, we have skin, we have eyes. I think that's it. So that's 4 draw calls essentially. So 1 character is going to result in 4 draw calls. So is 300 characters still going to be 4 draw calls. You can do sort of instance skeletal rendering with a single draw call due to indirect rendering and just using shader storage buffer objects to store all your model transforms and your bone transforms and things like that. So while I'm in the sort of like rambly, just code explaining mood, I'll go ahead and show a part of my engine that kind of deals with this, the character renderer. It's not skeletal renderer, it's kind of specific to characters right now. Maybe this could be genericized into sort of a skeletal renderer, but I'll show a few parts of this and kind of talk about how we can get this to work so efficiently. And then finally, I'll show you guys some in-game stuff and show that it is in fact performing pretty well. So this character renderer you call frame begin every time. And the way I have it set up, you need to track how many characters you're going to be rendering. You need to track the total number of joints that you could have, the maximum number of joints. Like this is without any like skeletal LOD or anything you would do there. And the max number of submeshes you would have per shader. So you're actually, there's additional tracking going on in a character manager that I won't show that's kind of tracking this stuff as characters get added and removed to the scene. This just makes it a lot more efficient because we can resize our sort of GPU data buffers all up front and make sure we have the right amount of space available in our map buffers to make it super efficient. So we'll go into this. At the very beginning, we frame begin the resources. This is sort of just our buffers. So if I go to the resources here, you'll see there's a few buffers. We have our bone transforms, we have our model transforms, we have per shader buffers. And then these per shader buffers are things that are like, obviously for each draw call. So you have all your draw commands for that draw call, these draw elements indirect command. Google indirect rendering. I'll probably talk more about it later. It's an amazing thing. You can also look for ASDO rendering, talks more about it in OpenGL. And I think this is sort of something that Vulkan does by default. But this just has all the information about how you would draw a particular mesh using just a buffer of memory. So you can have all of your meshes packed into one big buffer, and then you just sort of point to that part of the buffer and put that into this draw command, and then it all gets packed into basically one draw call. All the draw commands get rendered together. In addition to that, we have the submesh instance data, which is for each actual submesh, like a head, a hand, a torso, a hair, right? They have additional data. And we try to pack this stuff really small because obviously shader bandwidth or GPU bandwidth is really important to keep as small as possible. So we managed to pack this into 16 bytes per submesh, which is pretty good. So this is just indexing into all our different buffers, right? Like we have our model transforms the start of our bone transforms, start of our morph data. This one is using more bits just because there's a lot more of these, but this could probably be packed down as well. And then some additional data about like variance. We have the concept of variance where you can actually have like different skin textures rather than the basic skin texture. This gives that kind of information there. And then this is not being used. I thought maybe that'd be useful, but you'll notice we also have these custom bytes. These are just like random extra bytes that you can use for shader specific data, like hue for hair, for value for hair, something else. Lots of different things you can kind of pack into these 3 bytes. And then obviously if this isn't enough, we can add an additional data buffer to put whatever extra stuff that some crazy shader might need to do. So let's go back up. So frame begin is just going to set up all this stuff. This frame begin is going to allocate all these GPU buffers. We have this nice handy little GPU streaming data buffer for things that are supposed to change every frame. So it will, optionally reallocate with sort of a fuzz value. So it's not reallocating every time something changed. And then this is using this super efficient, like triple buffered streaming buffer upload mapped buffer thing that you can do that is probably the fastest way to get streaming data to the GPU, things that are going to change every frame. So that's our frame begin. And then when we actually add the character, there's a bunch of stuff that happens in here. So the model manager is going to one by one add these characters, and these are going to create those draw commands. It's also going to do animation and things like that. So we do our visibility check, right? That's going to be important. Even if it's not visible, we're still going to run this task. We have a thread pool that's going to queue this into a high priority task, and it's going to burn through all these tasks on all of our threads each frame. All high priority tasks have to finish that frame. We obviously have different thread priority tasks that are lower, and those can, take multiple frames to finish. So a lot of crap in here that, if you don't like my code, I'm sorry. But the animation instance is updated every time. So this actually handles there's animation machines, animation state machines that get updated here. This updates every frame. This is why we needed to call this even if we're not visible, because you want to actually update that internal state of the animation, even if it's off camera, because you have states that are transitioning to different things. You want to make sure you're actually tracking what's going on. You don't actually have to update those poses, but you do want to at least update the state of your animation, essentially. And then if we are visible, we do a whole bunch of crap. We're doing, we're building our model transforms pretty efficiently, and then we're kind of building all of our submesh data. So you can see here's that custom data I was talking about where we set those custom bytes. This is how I'm getting the skin tone, the hair color. It looks like for the eyes, we're doing either left eye or right eye, and then we're doing iris, pupil, and sclera color and hues, and we're packing all that in as few bytes as possible. We managed to get 6 values into 3 bytes because we're using 5 bits for value and only 3 bits for hue, and 5 bits for hue and 3 bits for value, and that's really all you need. It still looks just fine. And then this input set that we decide is just obviously based on this enum here, this material shader custom input data. So the shader itself right now just kind of specifies what input set it wants. There's probably smarter ways to do this, but then if you wanted to add a new shader that's doing something different, you would just add a new value here and handle whatever custom data upload you wanted to do here. That all gets packed into draw commands. So we build up these draw commands using our level of detail. So there's different LODs for the model. They're all kind of packed together. So to show that, let me undo that. So let's go back out and turn on all the submeshes. Let's just reset to the normal base era. So I have somewhere in here, an LOD. So you can change the LOD, and you can see it gets really messed up, right? But what's happening is it's decimating the mesh. We're just using sort of an auto-generated LOD system. These are not hand-authored, but it doesn't do that unless you're really far away. So if I start moving the camera, you probably can't really tell in the YouTube video. About right here, I think, is when it pops down. But because it's so small on screen, you don't notice it, right? And you're getting a twofold bonus from that. Obviously, less vertices is less vertex processing time, which is really nice. But also, if I put on, again, oh man, this is a little bit of a mess. If I put on the wireframe view, the actual triangle density on screen, the number of these lines that you see between triangles is actually increasing what's called pixel overdraw between these triangles, because these pixels here are getting double shaded once for each triangle. So if you don't do this LOD when you zoom out really far, even here, I could probably start popping into a lower LOD here that I'm not doing. It kind of pops, I think, about right here. you get a lot of that pixel overdraw. And especially if you have triangles that are like 1 pixel size, it gets really, really, really bad. So something to pay attention to anytime you're doing anything is make sure your LODs are really good, or you're just gonna have really bad performance. Anyways, and then after we build those draw commands, we have a little extra thing for grabbing submodels. I'm not sure if this is how I want to do this long term, but this is actually grabbing those swords, shields, things that are sort of just attached to the player, and it's returning those because the model manager is going to then pass those to a separate renderer. Like I said, maybe a better way to do this, but I liked being able to do this sort of in this main render loop because everything's in cache already. I've already got all the bone transforms ready to go, so I can just kind of grab that and pass it off to something else really simply. And then finally, when we actually go to render, so I have render debug. Render debug is if I want to like turn on, for example, TBN matrices if I want to see like my tangent by tangent normal, which looks really bad in wireframe, but you can see this will let you kind of inspect your normals and things. It's really good to add something like this to your engine if you don't have this, because this is a common bug, is like you import a model and you do some kind of transformation thing wrong. Like you're trying to convert to Z up instead of Y up and you just break it, and then your transforms are all facing the wrong way. Your tangent space matrices here, the TBN matrix for doing normal mapping. So the render, what it does is it's going to wait for jobs. So we have, of course, a thread pool running in the background. And essentially, the way I have it working right now is the main thread's going to try to help out. So if there's a bunch of high priority tasks queued up from all these character models, the main thread will start to process some of those until we've finished all the jobs. And this job count is just an atomic variable. I haven't taught multi-threading, I realize. So if you're just fresh off of all of my other videos, this is probably a very confusing video for you. But some of my videos are going to be this way. And then once all of that's finished, we can then finally render the thing. So we flush all of our buffers. So this is flushing all of your GPU streaming buffers, all that stuff to the GPU. And then we're binding everything with, right now we're just always using shorts for the index type because we don't have really big models. And then rendering. So this is, you can see num draw commands per shader. Basically for each, this is a vector of the number of draw commands for each shader. So if there's 4 shaders, there's going to be 4 elements in this vector. So we'll essentially loop 4 times and do 4 draw calls. And this is just going to call render, which is just going to do glbind vertex array on our mesh vertex array object, make sure our shader's bound. And then it's just going to call multi-draw elements indirect. This is the magic secret sauce, amazing function that makes everything faster if you use it correctly. Again, make sure you research that stuff. So that's like a pretty deep technical dive, at least for the low effort ramble that I'm doing here. I'll go ahead and show what this looks like in game now. So sort of bringing it all together, I have this character debugger in game that'll let us kind of mess around with things. We're playing with combat, trying to figure out combat right now. Just like before, we can kind of tweak everything here. So I'll just make I'll randomize. There, we are now this person. And that rebaked the mesh. It updated the renderer, and now it's drawing very efficiently, right? So FPS is 60 at the top. Game thread is sitting idle at 3.5 milliseconds, which is, I'm not even sure what it's doing right now. But what we can do is spawn a bunch of NPCs. So I'll grab NPC characters, I'll turn off AI, and I'm going to spawn a bunch. And we're going to just go crazy with this and just see what it looks like. I'm going to have some far away, some close, because obviously if I dump them all close, then we're going to have really high vertex count because we're not getting that LOD kick in. So let's see where we are. So game thread up to 8 milliseconds. It looks orange, but that's actually still pretty good. And then we have 400 characters. So let's keep going. Keep in mind, this is 400 characters that are all animating as well. They are skeletal animated. And again, this is 4 draw calls for everything. And these are all on screen. If I move off screen, obviously they stop rendering and it gets a little bit more efficient. Game thread now at 70%. And I can tell you most of that from my profiling is actually not from like character rendering stuff. It's from physics right now and the character controller, which both could probably be optimized a little bit. Job for another day. But you can see we got all these characters, almost 700 characters, probably more than we're going to be putting, like, not trying to make Bannerlord here, but we probably could with this technology, right? All these people are animating, they're all, having completely different morphs, completely different hues and colors and all that stuff, and it's 4 draw calls. So that's that. This has been my TED Talk on character rendering and morphs.